Okay, angle to launch number 1. So, if you took your notes a little while ago, you might want to just have those notes nearby to you, review them, so you remember what we are doing here. The first thing that we need to do is take this launch velocity and break it up into its components. So I'm going to do that right here. So this is 1.5 meters per second, and I need to find the horizontal and vertical parts of that. And this is 20 degrees right here. So this is going to be my, whenever I find this, that's going to be my constant horizontal velocity, and this is going to be my initial vertical velocity every time. So when I make my vertical and horizontal columns of info, get those set up right now. What do I usually put first here? Vx. Of course, the order you write them down in doesn't matter, but I try to be consistent. So this is going to be your constant horizontal velocity, and this is going to be your initial vertical velocity. So get out the old calculator, make sure you are in degree mode, and oops, you can turn your calculator off. Then 1.5 times the cosine of 20 and 1.5 times the sine of 20. And you can see there's the bigger one, 1.4, going to be right here, and then about 0.5, you do 0.51, whatever you like, is this one here. So make sure you get those in the right place. Do this very carefully. You just go slapping those numbers around, probably not going to work out too well for you. Okay, now we're ready to do some, oh, no, we're almost ready. So this thing is, the edge of the ramp here is 1.2 meters above the floor, ground, whatever it is. Excuse me. So it is going to have a delta y of 1.2 meters, but that is 1.2 meters from here to here. That is going to be negative. A lot of these projectile motion problems, just like free fall problems, have negative delta y's. You have to be careful about that. Well, if you want to get it right. Alright, so here I'm going to do delta y equals 1/2 at squared plus vit, and that's negative 1.2. That's negative 5t squared, and that's 0.5t. And you can see I've got was doing some other problem like this, so I'm just going to change these numbers. That's going to be 0.5, and then I'm going to add that to the other side, 1.2, and I'm going to see my window. That should be fine. 0 to 10 for the times, that's going to be good, and then negative 10 to 10, that's fine. Anything that just, so long as you cross your y-axis, so you can see where it crosses, so long as you have a negative and a positive. So I'll graph that, and it looks like it crosses pretty early there because this thing's not going that fast and it's not that high up, so no surprise there. But I'm still going to just do my second calculate, looking for the zeros. I'm still just going to type in 0 and 10 because why not? You could do 0 and 1 if you're confident about that. 0 to 10, that's 0.54. So that's the same time for that. And then I know that delta x is equal to Vx times t. I'll round that to 0.76 meters. there we go. That's how you do it. All right, let's do it again. Now the ramp is tilted downward and the sphere leaves the ramp at 1.5 meters per second. Same speed, but it's tilted down. And 15 degrees, a little bit different angle there. So here's my launch. And notice that this is down. That's going to give me a negative initial velocity. So this is 1.5 meters per second. Go ahead and do 1.5 cosine 15 and 1.5 sine 15. 1.45 and 0.39. 0.45, 0.39. And that's going to be negative. Okay, so set up my info here. So my initial velocity is 0.39 meters per second down. I don't know the final velocity. My delta y is going to be, it's going down negative 0.90 meters. And horizontally, I have my Vx, 1.45 meters per second. That's my constant horizontal velocity. Looking for that delta x, and I'm going to find the time over here and bring it there. Okay, so delta y equals 1/2 at squared plus vit. And here I've got my delta y is negative 0.9 equals negative 5 t squared minus 0.39 t. So just modify this one. So here I got minus 0.39 now, minus 0.39 x, and then I got to add that plus 0.9. That looks good. I know my window's all set, and that is going to be an even smaller time because this had a head start toward the floor, and it's a little closer to the floor also compared to number 1. So we're expecting to get a time that's less than that. I'm going to hit the ground a little earlier, but I can still do the same thing here. Second calculate, looking for the 0. And the left bound will be 0, right bound 10, because that's what my window is. That works just fine. So 0.39 seconds. And then I know that delta x is Vx times t, constant velocity in the horizontal direction. And that gives me whatever 1.45 times 0.39 I'll call that 0.57 meters. All right. Number 3. A projectile is launched from a 10-meter tower at an angle of 20 degrees from horizontal at a speed of 100 meters per second. And we want how long is it in the air, find the time, how far does it go, and then what's the maximum height of the projectile. We'll talk about that in a sec. These are just the same things that we did in 1 and 2. So let's see. We got it's launched. I'm going to make a little diagram of this. It doesn't have to be, fabulous diagram or anything, but this is a 10-meter tower, and it's launched at 20 degrees at 100 meters per second. That is fast. That's like 200 miles an hour-ish. Okay, so I'm going to need to break the 100 up into the components using sine and cosine. I'm going to call that 94 and 34. 94, oops, I said 94 and I wrote 93 meters per second, and 34. And I put them the wrong way around too, because obviously that's, I think, part of the advantage of doing them on the calculator at the same time. Seeing both numbers, you can see which one should go with the longer leg of your triangle, right? Okay, so I think I'm ready to set up my vertical and horizontal info. So acceleration is going to be negative 10 meters per second squared. Initial velocity is, this is in the vertical direction, so it's 34 meters per second up. Don't know the final velocity. The delta y is, it's starting at this 10-meter tower, and then it's getting to the ground, so it's going to be negative 10. And then we're going to find the time. And the horizontal, I got my Vx, which is 94 meters per second. And I got my delta x, well, I don't got it yet. I'm going to look for it, going to find it, going to find the time here, bring it over here, and then find that, just like we did in 1 and 2. Alright, so here I'm going to do my delta y equals 1/2 at squared plus vit again. Delta y is negative 10. That's always negative 5. T squared. And then the initial vertical velocity is 34 t. Alright, so got plus 34 t. Oops. Try that again. Plus 34 t and plus 10. So that looks like it crosses there, and it's still between 0 and 10, so I can do exactly the same thing. Find my 0, left bound 0, right bound 10, 7.1 seconds. And now in this direction, so that's the answer for part A, right? For part B, I know that my delta x is equal to Vx times t, and my Vx is 94, and my time is 7.1. If I'm rounding to two significant figures, I would call that 670, and if you wanted to do 3, it'd be 667. Either way is fine. That's my answer for part B. What's the maximum height of the projectile? Well, to find the maximum height, that's finding the delta y when the Vf is 0. Max height is find delta y when Vx is 0. Right? You're going to have to remember that. The maximum height is when the vertical velocity goes from positive, which is going up, to negative, going down. So that's when it's equal to 0, right? When it changes from positive to negative. So for part C, we just have to redo the vertical part. Acceleration is still negative 10. The initial vertical velocity doesn't change. That's still 34 meters per second. The final velocity, we're going to set that equal to 0 because I'm looking for that max height, and I want to find the delta y. Right? So that is going to be my Vf squared equals Vi squared plus 2a delta y. That equation. Vf squared is 0. Vi, and then I've got 2 times a, that's, I guess I could have put that as minus 20 delta y, right? My 2a. So when I do the algebra here, that's going to come over to this side, or this is going to come over to that side. So it's 34 squared divided by 20, right? That's about 58 meters is the delta y. Now here's a tricky thing about this. This is, if you make this mistake on the test, whenever that happens, this is going to be a small penalty, like maybe 2 points or something like that, not more than that. So this is the delta y, but what's the maximum height of the projectile? Well, it started on top of a 10-meter tower, and then the delta y is 58 meters. So what's the maximum height? Its height changed 58 meters from the 10 meters where it started. So it's actually 68 meters, because the delta y is 58 and it started on a 10-meter tower. A little tricky there. All right. Number 4. A water balloon is launched at a building that's 24 meters away, so that's this 24 meters. What is that? If you think about like the whole, all of this vertical and horizontal stuff, what is this 24 meters? Where does that fit in? Well, it's meters, right? So there's only a couple of things that it possibly could be if you think about the units. It could either be a delta y or a delta x, right? And delta y is up and down, delta x is across, so this is our delta x. Vx, delta x, and time. With an initial velocity of 18 meters per second, don't make the mistake of thinking that that means that's this. It's not. This is at an angle of 50 degrees. So I have to take that 18 meters per second and break it up all right. So 18 meters per second times sine and cosine of 50. And the bigger one is the one that's across from the 50-degree angle, 13.8, 11.6. This is the initial vertical velocity, 13.8. This is the constant horizontal velocity. All right. At what height will the balloon strike the building? That's the delta y, right? And now this, unlike the last problem, this one's just starting from the ground. So delta y, that really is just the height there. Okay, so I need to find, this one's a little different. I have two things over here, and I'm going to find the time on this side. So I know that over here, delta x equals Vx times t. The delta x is 24 meters. I don't know why I wrote the meters there. I don't usually write the units when I'm doing my algebra. 11.6 times time. So that time is going to be 24 divided by 11.6. I'm going to call that, what, 2.07 seconds. Bring that over here. And at what height, that's going to be my delta y. Kind of running out of room here. Where shall I write this? How about right here? Delta y is equal to 1/2. You should do this on a separate sheet. I'm setting a bad example here. I'm trying to cram it all in here. So delta y is equal to -5 times t squared plus vi t. -5 times t squared plus VI times t. So 7.14 meters. That's how high. If the balloon misses or shoots over the building, how far will the balloon land from its launch location? What's that about? Well, if we want to know, to figure that out, we got to go back and say that's not the time it takes to go here, that's the time it takes to go all the way. So that is figuring out the time with these three things, right? This is more like what we did in numbers 1 and 2. So for that, this is for B. I have the vertical stuff is going to be acceleration is -10. Initial velocity is the same. We got the square there. And my delta y, if we're talking about going from here and missing the building and getting back to the ground, that's from ground to ground, that is a delta y of 0. That is important that you understand when that's going to be equal to 0. And I got to find a new time here and then bring that over to the horizontal side where the horizontal velocity is still 11.6. And I'll have a new time and I can find the delta x. Sorry, I switched the order of those, but it doesn't matter. All right, so here I've got delta y equals 1/2 at squared plus vit. Delta y is 0, -5t squared plus 13.8 t. You can graph that if you want. This one, because that's equal to 0, you could factor a t out and do the algebra that way. That also works. But the graphing works 100% of the time, so why not just be consistent and do it that way? Of course, you have to type in the right stuff. Make sure I delete anything else that's in there. All right, there's the crossing right there, so I'm going to second calculate, look for that 0. It's somewhere in between 0 and 10. 2.76. And that's the time here, 2.76. So delta x equals Vx times t. And it's about 32 meters. Okay. If the balloon can be launched from less than 24 meters away from the building at the same speed and angle and still hit at exactly the same height you calculated in part A. Oh, sorry, this is not if. It can be. Determine this second launch location. So what's that about? Well, the first one, if you imagine like the trajectory of the balloon, it's going like up and then back down again and hitting here. So apparently, like if you moved, not apparently, if you scooted closer, you could like get it on the way up, right? So this thing, it's at the height of 7.14 meters. That happens 2 different times. So what we need to do is find the other time that it's going to be at that height. Okay, so how do we figure that out? And if you're thinking, whoa, this is hard, this is a little trickier for sure, probably harder than test question is going to be. So in the vertical direction, still on planet Earth, so that's still -10. VI is still the same thing. And delta y is equal to what we found in part A, which was 7.14. And the time is going to be something different. So delta y equals 1/2 at squared plus vit. My delta y is 7.14, and that's still negative 5t squared, and my initial velocity is still 13.8t. If you're thinking, well, how's this different than what we did in part A? Let me show you what this is going to look like when we graph it. Negative 5t squared, I've got the 13.8 in there, and I'm going to subtract that over to the other side, and I'm going to look at my graph. So you can see there's two different times that we get here. This is the one that we found. That's the 2.76 right there. But now there's another time. Sorry, that's not that 2.76. It's the 2.07, right, that we found in part A. But you can see there's another time. So now we have to be a little bit more careful. If you do second calculate, let's just see what happens. If I go to the 0 and I tell the calculator find it from 0 to 10, yeah, it found the wrong one, right? It found that one. So we're going to have to be a little bit more specific about where we want it to look. It looks like that's before 1, so I'm going to tell it now to do it again. Find me the 0, but I want this other one, which is between left bound 0, right bound 1. That's 0.69. And I'm going to bring that over here. My Vx is still 11.6 meters per second. Uh-oh, my pen's dying. Time, oh no. Oop, just switch colors. And the time is 0.69 seconds. So my delta x is Vx times t. So what does that mean? It means that if you want to hit that same spot but on the way up instead of the way down, you can do it by moving your launch location up to 8 meters, 8.00 meters. Right, so going back to the original problem, this is 24 meters away, so if you launch from 8 meters away, you're going to hit that same spot, just on the way up instead of the way down. That makes sense, right? Cool. That's number 4. One more. Football is kicked from the ground 40 meters away from the goalposts. Let's make a little picture of this. Football, here's the goalposts there. This is 40 meters away, so that's going to be my delta x, right? That's a horizontal distance. The crossbar, which the football needs to go over to score, just in case you didn't know that about football. Just thought I'd tell you that. So the crossbar is 3 meters up. That's about what they are. I got just a wee bit more than that, maybe. If the ball takes off at an angle of 40 degrees from horizontal at a speed of 25 meters per second, then I'm going to do some math here, find some stuff. So it's going to be kicked at 25 meters per second, and the angle is 40 degrees. So I need to break that up into the two parts. 25 cosine 40 and 25 sine 40. All right, this is the bigger one, cosine. That's the one adjacent to this. Let's call that 19.2 meters per second, and then I got 16.1. Okay, I think we're ready to set up our vertical and horizontal information. All right, VI. Vx. And then I got delta x here and time. And in this problem, I know what the delta x is. Oh, wait, nope, just kidding. So you have to be really super careful with this, because you just need to make sure you understand what information you're putting there and what you're going to be able to find when you set up the information in that way. So how long is the projectile in the air? Well, it's going to go, I mean, unless it doinks off the crossbar, it's going to be in the air for however much time to get back to the ground. So for part A, the delta y is 0, not 3, right? Because I'm going back to the ground. And the delta x is not 40 because it's going to go over the crossbar and it's going to land somewhere over here, right? It's not going to land there. So we're going to use that information, but not right now. Okay, so this is just a ground-to-ground launch. How long is the projectile in the air? Let's set that up. I got delta y equals 1/2 at squared plus vit. And put my numbers in here. So 0 equals -5t squared plus vi is 16.1 t. You can put that in and graph it. And after you do that, you should get about time is 3.22 seconds. And that is the answer for part A. For part B, how far does it go? Well, delta x is equal to Vx times t. So this is the same thing we've been doing in all the other problems, right? So 19.2 times 3.22, it goes about 61.8 meters. Does the ball clear the crossbar? So it lands out here at 61.8 meters, and you're like, oh, that's past 40, so that's great. But we don't know if it went over or not. So how do we do that? Okay, so we got to set this up again and just be careful about what we write down. The initial velocity is still 16.1 meters per second. That's a 6 there, sorry. And final velocity, I don't know. We're not going to find that. That's what we use when we were looking for the maximum height. And we could find the maximum height, and if the maximum height was more than 3 meters, we would know at least that it had a chance, but it still wouldn't tell us this. What's the delta y? So there's two different ways you can do this problem. You can set the delta y equal to 3 meters, and then you can find, just like we did with the water balloon, you can find the two different times when the ball is going to be at that height, and see what, then use those two times with the horizontal velocity and see how far you are. So if it's at a height of, let's see, I think this is the harder way to do it, but I do want to tell you about both ways. So if you find the time when it's at 3 meters for the second time, and then plug that in your horizontal side, and then see what where it is, if that distance, if that horizontal distance is greater than 40, if it's at a height of 3 meters the second time it's at 3 meters, that's when it's coming down. If that's bigger than 40, then you're good. It's over the crossbar. I think that's a little trickier. The way that I think is a little bit easier to do this is to make the delta x equal to 40 and see how long it's going to take the ball to get there, and then use the time over here. I think that's a little bit easier, but you can approach it in both different ways. What is the time here? So my delta x is equal to Vx times t. Delta x equals Vx times t. So I'm going to 40 divided by 19.2, that's going to give me my time, 2.08 And I'm going to bring that over here. And now I just have to figure out, I know how long, I know that it's going to be at this distance of 40 meters at 2.08 seconds. So how high is it going to be? I can find this. If that's bigger than 3, then we're over the crossbar. So delta y equals 1/2 at squared plus vit. So what delta y am I going to get? Is it going to be bigger than 3? This is exciting. -5 times there's a time squared plus vi times t. Right there. And here we go. Let's see. -5 times 2.08 squared plus 16.1 times 2.08. What do you think? Is it going to be good? It's good. It's really good. I mean, that's at almost 12 meters, so it's way over the crossbar, right? Which happens sometimes when you're kicking from not that far away. It goes way over. So the delta y is equal to 11 let's say 86 meters. It's up and it's good. All right.